Now we're going to work with a cylindrical conductor. The picture I'm going to draw is going to look identical. We have A, we have B. This one's going to have a charge positive Q, this one's going to have a charge negative Q. The difference is this. This is a sphere. This is a cylinder coming out like this. Okay. So the cross section looks the same, but this is an extrusion, whereas that's rotated around an axis. So this is a sphere, this is a cylinder, which comes out toward you. And our goal is, again, figure out the capacitance of this capacitor. We're going to assume that L is much, much greater than A or B. In other words, the length, where L is the length of the conductor. In other words, the end effects of this are negligible. Just so you know, this is a coaxial cable.
Those were so poorly designed. It's one of the
So this is a coaxial cable. Our goal is to figure out capacitance. The equation for capacitance, Michael, is what? The equation for capacitance, Michael. Q over
V.
Change in V stands for what, Michael? The electric potential difference. Q is just the charge on one of the positive conductor plate. So we need the electric potential difference. The electric potential difference between A and B, or this is going to be the integral from A to B of the electric field, the negative of dot d, dr, or d, doesn't really matter, dr. Which means we need the electric field that exists right here between the two cylindrical conductors. When we did this before, we had an equation for that electric field. We don't now. What do we need to do in order to figure out the electric field that exists between these two cylindrical conductors? Yes, we need to use Gauss's law. So we are going to use the electric flux is equal to the closed surface interval of E dot dA, which is equal to charge on the inside divided by E naught. I feel the excitement emanating from the group. Trust me, Gauss's law comes up a lot. We need to now draw a Gaussian surface. The shape of our Gaussian surface is going to look like this. It's going to have a radius that is a radius r, where r is between A and B. It is a cylinder that looks just like this. Nick, walk me through. Just get started, please.
So, surface integral of E dA cosine theta. Cosine, well, theta would be 0 for like side part of it.
For which part?
The side.
The side, okay.
Theta would be 90 for the ends.
Notice that for the ends, the dA is either going to be completely toward you or completely away from you, which is at a 90-degree angle to the electric field. So all we're talking about here is the side, and for the side we have a cosine of 0, so we end up with a closed surface integral of E dA for the side. Keep going.
So E is constant, so E surface integral dA, and that just makes it EA.
Area of what?
Side.
The side of the Gaussian surface. Okay, I'll just keep the same thing on the left here for now. E naught Q in, E naught Q in, E naught Q in, E naught. Okay, so we have the E, the electric field, which we're trying to solve for, multiplied by the area of the side. What is the area of the side of the Gaussian surface? Please. 2 2 pi r times L. So 2 pi r times L is equal to, now we need to deal with the charge on the inside. Look.
Plus Q. Just Q.
No, this is going to be the charge inside the Gaussian surface. The Gaussian surface does not run infinitely long. It's only a small portion of it. So we need to know. It's not seeing it. Who can help us out here? Sierra?
Surface charge density.
It's actually not going to be surface charge density in this particular case. Also not going to be volumetric. Linear, because we have essentially a line here. Linear charge density equals Q over L. Therefore, the charge, it's also equal to the charge on the inside divided by the length of our Gaussian surface. So Q on the inside, the charge inside our Gaussian surface is equal to lambda times L. So it's equal to lambda times L divided by E naught. That's right, ladies and gentlemen, people. Everyone brought L to the party. So the electric field is equal to, let's see, we've got to do 2 times 1 over 4 pi E naught times lambda over R, or 2k lambda over R is the electric field. Coming back, we now need to figure out the electric potential difference. The electric potential difference was equal to the negative from A to B of 2k lambda. Actually, we'll do it in 2 steps, just to make it clear. The electric field dot product dr. We have negative from A to B, 2k lambda divided by R dr, cosine again of 0 degrees. Because as we go from here to here, the electric field and the dr are in the same direction. We can now figure out let's see, the electric field is, or electric potential difference is equal to negative 2k lambda, are all constants from A to B of 1 over R dr. Integral class of 1 over R, the natural log of R. So natural log of R from A to B, negative 2k lambda natural log from B minus natural log of A, which is the same thing as 2k lambda natural log of B over A.
We don't have any more video sheets.
Finish. Okay, so we then, this is the electric potential difference. Capacitance equals charge divided by electric potential difference. So we have charge divided by negative 2k lambda natural log of B over A.
Come to the
Natural log of
office.
B over A, positive or negative?
Eric Fox, Aaron Zimmer,
Positive. So we
Aaron
need to
Dunn,
take the positive value, just the
Allison
absolute value
Robinson,
of
and Rachel
the
Coleman.
electric potential difference. Charge is equal to, we know from what we've got over here, charge is equal to lambda times L, the length of the whole thing. Therefore, we can substitute in here the lambda times L divided by 2k lambda natural log of B over A. Lambda cancels out. You get L over 2k natural log of B over A. Ladies and gentlemen, people, thank you very much.